What specific problem does the implementation of Gemma using sparse autoencoders, SAEs, aim to address in the field of model interpretability, and why is it significant?
The implementation of Gemma using sparse autoencoders, SAEs, aims to address the challenge of identifying meaningful internal activations within language models, which are often sparse and represented as linear combinations of vectors. This is significant because it enhances model interpretability, enabling researchers to detect and fix hallucinations, explain unexpected behaviors, and prevent manipulation by autonomous AI agents. By providing a comprehensive suite of SAEs across various layers of the Gemma models, Gemma facilitates more ambitious applications of interpretability, such as circuit analysis and understanding complex model behaviors like chain of thought and in-context learning. Furthermore, the release of these weights under a permissive license promotes collaborative research, addressing the current limitations of existing interpretability techniques that are often proprietary and difficult to scale. Overall, Gemma represents a critical step towards advancing the interpretability of large language models, which is essential for their safe and effective deployment.
Can you break down the workings of the Gemma sparse autoencoders, SAEs, step by step, including the roles of the encoder and decoder functions?
The Gemma sparse autoencoders, SAEs, operate by decomposing and reconstructing the activations from a language model through a pair of functions, the encoder and the decoder. The encoder function maps the input activations to a set of latent variables, which are sparse representations of the input, while the decoder function reconstructs the original activations from these latent variables. The encoder uses a set of linear weights to combine the latent variables, producing a reconstruction that is trained to minimize the squared error between the original and reconstructed activations. The Gemma activation function introduces a learnable threshold that determines which latent variables are active, allowing for a variable number of active latents at different tokens, thus enhancing the model's flexibility. Additionally, the training process incorporates an L0 penalty to encourage sparsity in the latent activations, ensuring that the model focuses on the most relevant features while maintaining a compact representation.
Could you provide a simple illustrative example of how the Gemma activation functions affect the output of an SAE during the reconstruction process?
The Gemma activation function operates as a gating mechanism that modifies the output of the sparse autoencoder, say, during the reconstruction process. Specifically, it applies a learnable threshold parameter to the pre-activations. Values above this threshold remain unchanged, while those below are set to 0. For instance, if a latent activation is computed as 0, 8 and the learned threshold is 0, 5 the output remains 0. 8, however, if the activation is 0, 3 it is zeroed out. This selective activation allows the SAE to focus on the most relevant features while enforcing sparsity, as only the latents that exceed the threshold contribute to the reconstruction of the original input. Consequently, this mechanism enhances the interpretability of the learned features by clearly delineating which components are active during the reconstruction process.
What are the specific computational and theoretical advantages of using Gemma over traditional ReLU and Top-K methods within this framework?
Gemma offers several computational and theoretical advantages over traditional ReLU and Top-K methods in the context of sparse autoencoders, SAEs. Firstly, Gemma allows for a variable number of active latents at different tokens, which enhances flexibility in modeling compared to Top-K, which enforces a fixed number of active latents. This adaptability can lead to better representation of the underlying data structure. Additionally, Gemma employs a learnable threshold parameter, enabling it to fine-tune the activation dynamics for each latent, which can improve the model's ability to capture meaningful features. The use of Gemma has been shown to provide a slight Pareto improvement over other activation functions, indicating that it can achieve better performance in terms of reconstruction fidelity while maintaining sparsity. Overall, these advantages make GEM-LU a more effective choice for enhancing the interpretability and performance of SAEs in language models.
How did you validate the effectiveness of the SAEs trained on the Gemma models, including the metrics used and the datasets utilized for evaluation?
The effectiveness of the sparse autoencoders, SAEs, trained on the Gemma models was validated through various evaluations, focusing on reconstruction fidelity and sparsity metrics. Specifically, the mean L0 norm of latent activations was used to measure sparsity, while reconstruction fidelity was assessed using two metrics, with evaluations conducted on 2,048 sequences of length 1,024 from the same distribution as the SAE training data. Additionally, the evaluation included tracking reconstruction loss and delta loss across different token positions to understand performance variations. The results indicated that delta loss was consistently higher for residual stream SAEs compared to MLP and attention SAEs, suggesting that small errors in reconstructing the residual stream significantly impact language model loss. Furthermore, the SAEs were tested on various subsets of the PILE dataset, revealing that they performed best on formulaic data like DeepMind mathematics and worst on multilingual datasets like Europarl, likely due to the training data's English predominance.
What key results were discovered regarding the sparsity-fidelity trade-off in the various configurations of SAEs, and how do these results contribute to our understanding of their effectiveness?
The key results regarding the sparsity-fidelity trade-off in the various configurations of sparse autoencoders, SAEs, indicate that wider SAEs tend to learn more latent directions and achieve better reconstruction fidelity at a given level of sparsity compared to narrower SAEs. However, the phenomenon of feature splitting suggests that wider SAEs may not always utilize their additional capacity effectively, as they might focus on learning frequent compositions of existing features rather than new ones. This finding implies that while increasing the width of SAEs can enhance performance, it may also lead to diminishing returns in terms of feature diversity. Additionally, the evaluation of delta loss and reconstruction loss across different sequence positions revealed that attention SAEs maintain lower loss in the initial tokens, highlighting their effectiveness in capturing long-range dependencies. Overall, these results contribute to our understanding of SAEs by emphasizing the importance of width in balancing sparsity and fidelity, while also suggesting that careful consideration is needed to optimize their configurations for specific tasks.